So we want to find the magnetic field due to this square loop. We're trying to find the magnetic field at point P, which is exactly the center of the square loop. So first, I want to impose my coordinate system. We're going to be using polar coordinates for this problem. First, actually, we're gonna make an observation. So since magnetic field follows superposition, we can just find the magnetic field due to this line segment of the square and multiply it by 4, since you can just add magnetic fields together. So it's the same thing as the magnetic field due to this plus the magnetic field due to this plus this, and yeah. And secondly, we can decompose our Biot-Savart integral into its scalar form because we can tell the direction using symmetry. So using our right hand rule, we point our thumb towards the current and then curl our fingers towards the magnetic field. So as you can see, if we go around the loop, our magnetic field, the right and left component of this magnetic field will cancel out, and the vertical, like the one pointing towards, like out of the board, the magnetic field pointing out of the board will conspire, will add up. Okay, so now we know that the magnetic field will be pointing outwards. So I'll just put it here, a dot with a circle representing the direction of the magnetic field. I will work further into imposing this coordinate system and calling our variables all sorts of stuff. Okay, so this length is a/2, the length of the square divided by 2. And we want to sum up the little bits of magnetic field due to the infinite amount of points in this line of current. How we would do that is by integrating using the Biot-Savart law and summing up all the magnetic fields due to this line. So we want to define this separation vector from your point P to your DL, the infinitesimal line of current through your loop. Not really the infinitesimal line, it's the infinitesimal length that your current goes through in this loop. So so this is a vector quantity, so I would like DL to point in the direction of the current to make calculations easier. So I would like to define the angle between your separation vector and your infinitesimal length as alpha. Let's call it angle alpha. And then the angle that you have traversed as you integrate will be theta. I will call it theta. Let's make it bigger here. That's theta. So now we can write our magnetic field equation. So the magnitude of your magnetic field is 4 times mu naught, 4 times because we're summing up the magnetic field due to 4 equal lines. Mu naught over 4 pi. We can actually cancel out this 4, so I'm just gonna do that now to make life easier. So it's mu naught over pi times the integral. So we're going to need to find our upper and lower bounds. We are actually going to do that later, so it clarifies, it's more clear. We do I dl vector cross r hat unit vector over r squared, your separation vector squared. Let's just call that a line integral. So it's a magnitude, so we need to take the magnitude of the right side as well. So we need to find the magnitude of this cross product, which is dl cross r hat. From linear algebra, you and we know that this is just the magnitude of your dl vector times the magnitude of your r hat vector times the sine of the angle between them, which is alpha, sine alpha. We know this is a unit vector, so this is just equal to 1, and dl, we can actually find it using differentials. So let's actually do that now. So if we define the length that has been traversed as you integrate this L, we can set up our differential. Actually, we can set up to find the differential L, dl, using trigonometry. So this is just tangent of theta is equal to length over opposite over adjacent, which is your adjacent is a over 2, so I'll just put the a on top there. And then you can differentiate both sides. Secant squared theta d theta is equal to 2 dl times a. So if we isolate dl, then we can just plug it into our integral. So it's just dl times a over 2 here. So that is our dl. So we found our dl. So we can just simplify that. Now I would like to I would like to express sine of alpha in terms of theta. So we could do this with a little bit of geometry. So if we draw our triangle like this, for you to reference, this is point P. This is just a section of our main diagram on the top left. Point P, this is your dl vector, and this is alpha. It's alpha, and this is theta. And we know in a triangle, all the angles have to add up to 180. So this is 90 degrees. So let's call this phi. So your phi is equal to 90 minus theta, because it has to add up to 180. This is 90 already. This is theta plus this angle is equal to 90. And then we can find the alpha using another identity, that this straight line has an angle 180 degrees on each of its sides. So alpha is nothing but 180 minus this phi angle, which is 180 minus 90 minus theta is equal to 90 plus theta. So this is alpha, so we need to find what sine of alpha is. I just erase this. So sine of alpha, but we know that alpha is just this, so we can just do sine of 90 plus theta. We could do further analysis with this sine of 90 plus theta, because sine and cosine is a periodic function. So I will draw, this is sine x, this is x-axis, this is your y-axis, and then sine of 90 plus theta means you're moving the whole graph to the left by 90 degrees, which is just this. But we all know this is the function cosine of x. So we can further simplify this sine of 90 plus theta using the identity. We can simplify this into cosine of theta. So that's another unknown taken care of, or actually not another unknown, that's another one of our components expressed in terms of theta. So we just need to find what r squared is, the separation vector here. So in a similar way we solve for dl and cosine theta, sine alpha, we can do some more trigonometry. So this time I would like to take the cosine of theta, which which is equal to the adjacent over the hypotenuse. This is a over 2 divided by your r, the magnitude of your separation vector. So we can isolate this and actually find the square of r. So just doing quick algebra, a over 2 cosine theta, and then you square both sides, which gives you r squared, 4 cosine squared of theta. So we found all of our components in our Biot-Savart equation in terms of theta. That means now we can do our integral. Actually, we do have to find our upper and lower bounds of integration first. So let me just write this down on top. A squared over 4 cosine squared theta. Let me just organize everything. Equal to a secant squared theta d theta over 2. Okay, so we need to find our upper and lower bounds. So in the square, so we have our square here. We have our point P, which is exactly in the middle. So this is a over 2. This is also a over 2. So our maximum and our minimum is represented by these two triangles. So this is theta L, theta sub L for theta lower bounds, theta sub U for theta upper bounds. So this is simple, pretty simple geometry. We can do this using tangents. This is also a over 2. These two are all 1, 1 root 2 triangles, so we can actually solve for theta U and theta L at the same time. Okay, so theta U is equal to 1, 1 root 2. So we can just solve for theta U using arctan. Tan of 1, which is pi over 4. And theta L is just negative pi over 4, because it's just the negative of it. It's just like negative 1 over 1. Okay, so now we have that taken care of. We can finally solve this problem. Actually, yeah, we just have to go through the integral. So theta U is equal to negative theta L is equal to pi over 4. Now I'm just going to rewrite our Biot-Savart equation. It's equal to mu naught over pi. Now we are replacing our variables. This integral goes from negative pi over 4 to pi over 4. And we need to multiply I. And then dl cross r, we already found the magnitude of it. This is dl, the magnitude of dl, which is a secant squared theta d theta divided by 2. R hat, the magnitude of r hat is 1, so I'm not going to write that. And sine of alpha is cosine of theta. And then we need to divide everything by r squared. So I'm just going to extend the division here. And r squared is nothing but a squared all over 4 cosine squared theta. And as you can see, a lot of our terms do cancel out, so I'll start doing that with a blue marker. So cosine squared and secant squared do cancel out. And then a and a squared, this will reduce the exponent to 1. And then this 2 and 4 will cancel out. Put 2 on the top. So now we end up with mu naught over pi times I'm just gonna pull out the constants, so times 2I over a times the integral of from negative 4 pi to pi over 4 I mean, of cosine theta d theta. So this is an easy integral to evaluate. It's just the integral, the definite integral of cosine theta is just sine of theta, and then you can put your bounds into it. So this integral is just sine of theta from -pi/4 to pi/4 with some mental work, or you can plug it into the calculator. That is equal to square root of 2. So then you end up with your magnetic field. The magnitude of your magnetic field is equal to 2 square root 2 of I. I'm just playing with the variables. Mu naught over a times pi. And 2, let me just make sure, 2 mu naught, 2 root 2 mu naught I. Oops, yeah. And then to get the vector form of our magnetic field, we found earlier that the magnetic field points outwards. So the vector magnetic field is nothing but the magnitude of it times the direction, b hat. We know b hat points outwards, so we can just say that our magnetic field is 2 root 2 I mu naught over a pi out of the page, out of the board in this case. Yeah, so that's it. That is the final answer.